Okay, let's implement Kruskal's algorithm. Now this is our pseudocode for Kruskal's algorithm. In order to implement this pseudocode, we need two things. We need a list of sorted edges and table which contain vertices and sets which corresponding vertex belong to. To simplify things up, I am going to add another structure called edge to represent edge in our implementation. So to represent edge list, you can use std_list data structure of edge objects and sort the list using any of sorting algorithms. But here I am going to use priority queue ordered by the weights of the edges. Now basically both these are same, but with priority queue we can have logarithmic time for sorting. Now for this vertex set table, I'm not going to use table. Instead I can represent this by an array. Let me show you how I am going to do this. Since we are adding nodes by sequentially incrementing id, we can consider any slot in array with particular index correspond to the vertex with id same as that index. So the value in the array correspond to that particular index is the set that the particular vertex belongs to. So in this way we can represent this vertex set table using single array. Okay, let's see the implementation. This is my edge structure which represents an edge. It has start vertex, end vertex and weight. And I have provided constructor to construct this object by providing these parameters. And in my MST Kruskal's function, which is a friends function for simple graph class, first I have created my vertex set integer array. And then I have constructed my priority queue, which will store the edges in a way that when it pops, it will pop the remaining minimum weighted edge. And then I am going to make our set. And here all I am doing is set all vertices belonging set initially to the particular vertex id. And also I have pushed all the edges to the priority queue as well. And then I am going to iterate until our priority queue is empty. And inside this while loop, I am going to pop the value from priority queue, which will pop the remaining minimum weighted edge. And then I am going to find the sets for n vertices for that particular edge. And then I am going to compare those sets. If those sets are similar, then I am going to ignore this edge and go to the next iteration. But if they are different, I am going to push this edge to our minimum spanning tree and then union the sets that those two n vertices are belongs to. That is done by this union set function. What it all does is it will iterate to our vertex set map and change the necessary slot so that all the vertices belong to the set that these two n vertices belong to one set. And finally I am going to iterate through our MST and print out all the edges in MST and also print out the total weight of MST as well. And in my main function for this video, I have reconstructed the graph that we have discussed in our presentation. And then I have called MST Kruskal function on this graph. Now let's run this example and see the outcome. Now you can see in this outcome, the total weight for MST is given as 37. And if you cross-check with the manual run in our previous presentation, you will find that the edges in this outcome are same as what we get from the manual run. Okay, that's how we can implement Kruskal algorithm. Thank you.